So James set up the Biomedical Sensors Lab in 2010 at Warwick to apply gas analysis techniques to medical applications. So the group has looked at an enormous range of applications, so everything from IBS, skin, colorectal, bladder, and pancreatic cancer, celiac disease, bile acid malabsorption, diabetes, tuberculosis, and many more. So James has got fantastic experience across these different diseases. He's also president of the International Society of Chemical Sensors and sits on the board of Science and Technology for Health GRP. So James's talk today is the diagnosis and monitoring of inflammatory bowel disease by the analysis of breath and other human waste. Thanks a lot, James. Over to you.
Hello, everybody. My name is Professor James Covington. I'm an electronics engineer from the School of Engineering at the University of Warwick. My talk today is on the diagnosis and monitoring of inflammatory bowel diseases by analysis of breath and other human waste. Okay, so what is IBD? Well, it is a truly unpleasant disease. It could cause, or it can be inflammation anywhere from the mouth to the anus. It's basically your body's response to the disease. It results in diarrhea, fever, fatigue. You get blood in the stool, you get stomach pains. It really is unpleasant. It comes in two forms, Crohn's disease and ulcerative colitis. Now, Crohn's disease basically can be anywhere in the gastrotract, whilst ulcerative colitis is basically the lower colon and the rectum. It's quite serious. So in the UK, about 1 in 210 people have it, which is about a total of 300,000 people. So it's quite a significant portion of the population. Now, one of the problems is actually diagnosis. So it has very similar symptoms to IBS, and diagnosis is actually quite invasive in the approaches they need to find out that you've got the disease. So it often takes a number of years to work out that you have IBD, and then a period afterwards to kind of start treatment and feel better. But importantly, there is treatment. So there's some effective ways to control the disease. However, throughout their lifespan, they get these things called flares. So the disease is either in an active state, in which there's inflammation, or in remission, where basically people can kind of continue with their normal lives. But it's really this 3-year diagnosis time, which is what we were focusing on. So I thought I'd kind of put a slide together of where we started this work and why do we think it was going to work. So IBD causes inflammation, okay? And we know that when people have inflammation, it creates VOCs, and these are things that we can detect. It also causes diarrhea, which obviously you can detect, and the disease causes changes in gut composition. If you think you've got your kind of digestive tract, that the disease is inflaming, etc., then clearly you're going to have reactions between the host response and your gut bacteria, and you can detect these changes. And you can detect these changes in all sorts of biological waste. We'll talk about more of that in a minute. So initial work on this kind of started in 2009. We looked at urine, and this is in collaboration with the University Hospital, Covington in Warwickshire. So, we basically tested a small number of patients. So we collected 19 samples, 10 with IBD and 9 controls. So one Friday evening, I drove over to UHCW and spent an hour and a half trying to find somewhere to park. And at 6:30 or 7 o'clock at night on a Friday, we started these experiments. And here is my collaborator at UHCW, Ramesh. Both of us kind of look older and have a lot more white hair now, but this was us being set up in the research labs there, and we were undertaking these first experiments. For this, we used a Serrano A320. So this is a traditional electronic nose, has 32 composite polymer sensors in it. So we put the urine in kind of a sterile bottle, and we modified the lid with a fitting, and we heated them up to about 40 degrees C, left them there for kind of 10-20 minutes, and then we pulled the headspace into the machine. And we kind of got this plot. So if you know a Serrano in any way, you know that you kind of get this type of PCA plot from it. It doesn't give you kind of axes of what the PCA plots mean, but this is what you get. And we saw these results. And in essence, we saw that IBD was different to normals. And this kind of spurred us on to do other activities. But this was kind of the first experiment there in 2009, 2010. So based on this work, we thought, okay, we'll have a go with breath. So we started collaborating with Elstone. This is before they were Elstone Medical. In the low 2000s, we said, well, maybe can we use their FAMES technology for this purpose? So we got some funding, etc. And what we tried to develop is a way of capturing breath. So this is well before the receiver and other types of systems. So we were trying to work out a good way of collecting breath sample from patients, and then how we were going to test it using a kind of FAMES system. So what we did is we basically made something like this. So we had a filter system here. So this was room air. So this was inside the ward at the hospital. The subject breathed in, so the air would come through the filter, through the first valve, and then into the subject's lungs. They would hold it for a second, and then they would breathe out, and it would go through into a 3-litre deadlock bag. And it had these kind of two-way valve systems in this filter. So this is the system we have. We're going to block a bit. So here's the filter. This was disposable mouthpiece, and these are the two filter valve sections, and the tube coming out. And this is one of the nurses using it. In use, we actually put a manual valve here as well. So as the patient breathed out, we twisted the valve about halfway through the process. And so we only captured end-tidal breath in the end. So we repeated this process again and again and again until the bag was filled. Now, one of the problems was that the machine was sitting in my lab at Warwick, and the samples were being collected at UHCW. So what we did is we stuck the bags in a -80 freezer after being collected, and then we shipped the bags back over to Warwick and we tested them on the day. So the nurses would collect the samples through the day, stick them in the freezer as they were done. Then we would dash over, stick the bags on dry ice, drive quickly back, and then test them. So how did we do the Lonestar testing? Well, at that point, we had a Lonestar system from Elstone, and we modified it to operate at, well, basically combine a positive pressure system and have a pump system at the same time. So one of the problems is, how do you draw the bag of wet, humid air through the FAMES unit at a constant rate? And what we did was we did something like this. So we had clean air coming in. So the total flow rate here was, say, 2 litres a minute, and then it had a pump on the end. Then we'd set this mass flow controller to 1500 millilitres a minute, and we'd draw 500 mils limit from the sample. So you could set the flow rate at the end using the pump. You set the flow rate of clean air, say 1500 mils a minute, and then you would pull sample air and mix it, and then through the machine. So this is kind of it in configuration. So this is the FAMES unit, this is the pump section in the bag, and then this is the heated inlet. So the air would get pulled in by the pump, and you'd take a small amount of the bag sample into the machine, and you'd run the kind of FAMES analysis. So in this case, we actually used nickel-63 in both the UV systems. So at the time, the nickel-63 source they used was quite high and needed a license in hospitals. So we were investigating whether or not a UV would work better. And the nice thing about the UV is that actually it doesn't respond to everything. So if what you're interested in is ionized by the UV, it means you're reducing the chemical noise. But on the other side, of course, if it's not, then you don't get any signal. So here are some demographics and example output. So for those who knows a FAMES machine, this is a kind of traditional output of a FAMES. This is basically equivalent to the magnitude of the electric field applied to the ionized molecules, and this gives you a measure of kind of mobility of ions. So basically down here you get all the ions together, so you just get what you can imagine a single big peak, and then as you increase the dispersion field, you start getting kind of separation of molecules. You can see kind of a few separate paths and a fair amount of chemical information from the breath. In terms of the group, we ran kind of 70 or 80 patients. They've got very similar age groups. They had, male female ratio was okay, etc. So they were a pretty good match between healthy volunteers and kind of IBD patients. So here are the results. So basically what we did is we took the raw FAMES data, we removed the background, and then we tried to identify discriminatory features within the kind of raw FAMES data plot. And we've got basically a process to do this. And you can look at the paper if you're interested exactly how we did it. So for those who are familiar, this is a ROC curve, which is often used in kind of medical work to show how good a test is. So sensitivity is basically the accuracy of the true positive rate, how many true positive samples it gets right, and specificity is just the measure of how many negatives it gets right. And these results were pretty good. So for the kind of how good or how bad our experimental method was, we thought that this was pretty good. And these are kind of probability plots for different combinations. So UCCD versus volunteers, so this is IBD versus volunteers. It's looking pretty good. We can separate them pretty well. But what you basically discover down here, this is UC versus CD, is it's not so good. So this isn't massively surprising because it's an inflammatory condition and both diseases are inflammatory conditions. So separating the two apart is very hard, and it might simply be to do with their magnitude on the inflammation. So we did that study. We thought it went quite well, and then we thought, well, let's try and do some more. So the problem with that experiment was that we had to collect the bags, stick them in the freezer, and then we had to ship them to Warwick, and this was a pain. And we're sure we're going to lose signal in that kind of transport stage. So what we decided to do is look at some kind of further experiments with IBD. And what we did is we basically sent all the equipment to UHCW and we ran the experiments there instead of running them here at Warwick. So in this case, we sent 2 instruments. We used a gas chromatograph eye mobility spectrometer, and we sent one of our in-house electronic noses. So this electronic nose is slightly different to kind of most common ones because it's designed for inorganic gases. So it's detecting things like CO, NO2, etc. And the kind of thinking behind this was that GCIMS is really good at detecting VOCs, whilst our eNose is very good at detecting inorganic gases. So we thought, well, let's bung them together and it should give us kind of should measure a wide spectrum of chemicals and we wouldn't miss anything. So just to kind of comment about how they work. So this, for GCIMS, many people will know how this works, but basically you get here's our person, we have a GC front end, so you have kind of some level of pre-separation, so you put lots of molecules into the GC, and it nicely separates them out into individual chemicals. So these kind of travel up here to a drift tube IMS system, which has a control gate. So you got your ionized molecule here, you open the gate, they then get pulled through this drift region, so you apply a very high electric field and these ions move along this drift area. And then the other way you put a buffer gas, which in this case was nitrogen. So you've got these ions going along, you've got your buffer gas, and where they impact, the momentum of the ion slows down. So basically the length of time it takes to get from one end to the other end is a function of this electric field and its collision with this buffer gas. The electronic nose was a much simpler affair. So we've just got an array of electrochemical sensors. We have a kind of pump at the bottom, and we're injecting our sample into the electronic nose chamber, and we get kind of some signal response from it. So this is kind of what you would see as a traditional electronic nose. So both experiments were done, or both instruments were used in these consultation sessions, and we use the same patients on both instruments. So this is our GCIMS system at the time. This is kind of an older model now. This has been replaced. This is one of my students here. This is the mouthpiece section, etc. So basically the patient has grabs hold of it, put it in their mouth, and has to take a single breath through the machine. So they blow through this disposable mouthpiece into it, and then a volume of their breath is collected and analysed. The eNose, well, that was a bit more of a palaver. So what we did is we collected, or we used these Marks BioVOC tubes. So these are basically look like big hollow tubes. And the user puts a disposable mouthpiece on it and blows through it, and it collects the last about 130 mils of air from their breath. So what we then did, so these are normally used to go onto tube, but we basically abandoned that and we put a big syringe on it, a big needle on it, and we put it in the top of our e-nose and a little motorized section. Here we go, this here. And basically it pushes the syringe down and puts the volume of this air into the machine, and you can get responses, etc. from it. So in essence, that we've separated out the collection process from the analysis process in the machine, and this worked very well. So this is a little section of the GCIMS output. So actually it's kind of larger and wider normally, but this is kind of one little section. So the dark blue here is basically just the background to what you get when there's no signal. And the red line is the response to clean air. And then these little splodges here are chemicals. So these are chemicals that are in the breath and we're measuring. This is kind of an acetone peak, etc. The e-nose gives you something like this. So the kind of big line here that's your CO2 levels. Here's your oxygen levels, and you see the other sensors responding, either responding well or responding very little to chemical components in the breath. But you can see we're looking at a kind of broad range of different inorganic gases, things that you wouldn't see as GCIMS. So we tried to do some chemical identification. How will it work? Well, that's a good question. But this is kind of this is the e-nose results. So we get big peaks of ammonia, sulfur dioxide, nitrogen dioxide. We have no reason, we have yet to link these with any kind of biological processes. But the ammonia particularly gave us very big differences in output, and was interesting. GCIMS, well, we got things like acetone, and we got, which is kind of a metabolic marker. 2-butanone is probably something environmental, and you have this butyric and ethanoic acid. Probably these are associated with some kind of fermentation process. So it could be the gut bacteria affecting normal function within the kind of gastro tract, and we're starting to see changes of this. So you can see we are seeing slight modifications in things like acetone levels against Crohn's disease and ulcerative colitis. And you would expect kind of metabolic changes resulting from this condition. So as before, the electronic did okay. GCIMS did much better. So we're kind of showing that mostly we're looking at VOC changes rather than kind of inorganic gas changes. The kind of IBD versus controls, the AUC is area under the curve, is very good with a good sensitivity and specificity. And these are really nice results. We're very pleased with these. And they show basically there's a clear difference in breath between IBD patients and healthy controls. But also that, and again, it's still hard to separate CD from UC. So there are still differences. That's much harder to do. The electronic nose here won, did much better, and don't have an explanation for this. But for the kind of VOCs, it does worse. So as this is kind of on other biological material, we've also looked at fecal matter for analysis of IBD. So as IBD results in kind of changes in gut bacteria, and we also have inflammation in the gut, there is the potential to measure these using kind of VOCs emanating from stool. So these are two examples, one for GCIMS and one for FAMES. And these are in collaboration with my Dutch colleagues, who basically discovered that those in Amsterdam were quite happy to give stool samples, unlike the UK. So the GCIMS study had very good numbers. We were collecting over kind of 400 or 500 patients. The FAMES was not so large, so it was an earlier study. And we also, for this kind of GCIMS studies, we had patients we managed to collect samples from patients in remission and samples from active disease state. So we had, which is really nice, we had both disease types that we could investigate. So because we have so many samples, we now kind of auto-sampled both of our technologies. So this is a Lonestar system with a MPS auto-sampler, a little heater box. And this was set up in a dynamic mode so we could kind of run FAMES, traditional Lonestar FAMES analysis. Our flavor spec course is fitted with a CTC auto-sampler, and that kind of helps out a lot. As you can see on the outputs, both GCMS and FAMES is much more chemical information. Still is a much more complicated biological material, and you have a lot more VOCs from it. So it is harder to deal with in some ways than breath. So these are kind of some probability. These are FAMES results. Again, the IBD versus controls is pretty good, and in fact, it's pretty similar to what we had for breath at this rate. And once again, CD and UC is much harder to separate. However, our GCIMS results are pretty impressive. So we're at sensitivities well above 0.9, very low p-values, and basically this is kind of medically relevant. So it's such a good result that with this large sample size and sensitivity to these values, it is clinically relevant. The kind of only interesting one from here, or another interesting point, is that you can't use stool to separate people from remission and active disease state. It's likely that both states have altered the gut, but active disease is a rapid change and you wouldn't see this. So the gut is basically averaging out these VOC signals and you get kind of this type of thing. So we also looked at using breath for monitoring of treatment. So they've got some new drugs online which are given IV. So these drugs are improved quality of life. You have to reduce visits or have reduced visits, and they have fewer side effects. However, we do have this problem that you can result in allergic reactions. So at the moment they take blood and try and measure this in blood serum, but can we do this in breath? So basically an alternative to this therapeutic drug monitoring. So we managed to recruit 26 patients into this, 13 with Crohn's and 13 with colitis at UHCW, and they were receiving these kind of drugs for their IV infusion. We collected 4 breath samples, so we had one at T0, 15 minutes, 30 minutes, and post-treatment. So because we couldn't get this machine near them, we actually in the end used the Marks BioVOC. We get them to breathe into the thing, and then we dashed over to the machine and injected it in manually. And this worked really well and kind of reduced the stress on the patient. And we found a number of molecules that got modified. This molecule here, 1-octane-3-ol, was consistently appeared in all the measurements, but we saw these kind of pentanoic and butanoic acid, which are kind of part of burning carbohydrates, etc. And these also was changed or modified through the course of treatment. So these are our results from it. So you can see that for Crohn's disease, we saw this big change in output, and ulcerative colitis, we see a much smaller one. But clearly this will be linked to the amount of infusion inside their bodies. And this variance is most likely to be associated with difference in people, different sizes, weights, etc. And really what we're trying to do now with this work is line this up with what we will see in serum and in blood. So these are some of our studies that we've done over the course of 7 or 8 years, and AUCs, etc. And in fact, breath and stool are very close together. So you don't have a great difference in sensitivity and specificity between these two biological materials. Of course, breath is much easier to collect and a lot easier to analyze than fecal matter. And therefore, in the future, maybe breath is the way forward. So IBD remains a really unpleasant disease that affects a lot of people. We're hoping that better diagnosis could reduce people's quality or improve people's quality of life, and closer monitoring would also help. So breath analysis could be a way of achieving this, either within kind of primary care or secondary care settings, or even at home. And really in the future, we'd like to do some larger multi-center breath studies to really understand these differences better. Finally, I'd like to thank many of my collaborators and my many students, etc., over the years who've worked on this project. And thank you.
I did have one quick question initially, or actually two very brief ones. So the ammonia result was quite interesting. First question was, do you have a sense of the concentration on breath for the ammonia?
So yes, so we use the instrument like an electron nose, so we didn't have to worry about ammonia concentration. But if we so desired, we could go back and calculate the concentration in ppm or ppb.
Okay, but it was detectable on breath, so it was
directly. So it was an ammonia sensor in the system, so there'll be some cross sensitivity, but it'd be pretty good.
Got it. Okay, thank you. The second question was for some of the models that were built where sensitivity and specificity looks great. Have those models then been tested in prospective cohorts and used independent samples there?
Ooh, okay. So most of the smaller studies were done with you had to use kind of cross-validation techniques because you didn't have the sample size. Some of the larger studies were split, but we are now doing more prospective work where we're getting more samples in. I suspect that the parameters are instrument dependent. So if we use a different machine or if we use some slightly different settings, then I suspect that we'll still have to go through another training phase before we can get to a kind of diagnostic stage. But we have done studies where we've done basically this type of thing, where we have samples we don't know, double blinded to us, at the end of the study and done that process, and it's worked quite accurately.
Right, okay, thanks. So we have a question from Alexis. Do we have a gold standard procedure for collecting breath samples? How much breath samples usually needed for test or diagnosis?
That's like, you know, how long is a piece of string type of question. So I don't know, or I'm not aware of any gold standards for breath testing at the moment. I think that
collection was the question, not.
Sorry, I just said, what did you? So you'll have to repeat it. I'll turn the volume up.
It was around collection because obviously there's different analytical techniques that can be used in discovery and validation. So the question is around sample collection.
So is there a gold standard for sample collection for breath? Is that what he's interested in?
Yeah.
The answer is no. I think that what happened with our studies is that the disease and the patient defined how we had to collect the sample. So it's not like we had a technique that we thought was really good and perfect and we could apply to every situation. We ended up, it's like the kind of infusion study. You know, the patient, you can't stick a machine near it, you can't put a receiver over the top, you can't do lots of things. And therefore the approach to sample collection is defined by the environment you have to operate in.
Okay, thanks, James. And obviously you mentioned receiver there as well. So if anyone's interested in sampling on the sorbent tubes for subsequent analysis, that is something worth looking at, and the team can send more info on that. Next question is from Roy Goodacre, who we'll be hearing from tomorrow. Roy says, I'm enjoying your talk, James. The problem with quoting low p-values is that the more samples you get, the better the ability to distinguish groups. This does not necessarily translate to clinical utility. You need to consider false discovery rates on multiple testing. What method did you use for this?
I agree with all of those statements. And I nearly left the p-values out for those exact reasons when I was writing the presentation. So I don't have a good answer to him beyond the only way to kind of get a true p-value is to test more patients, have a larger cohort, use multiple sites, multiple nurses, etc. And this will kind of give you a more accurate reading or an accurate value of kind of statistical parameters.
One kind of related question to that. Did you get a sense of the number of features that were included in analysis in something like GCRMS, for instance? And then which of those were actually on breath versus, again, what may just be present on instrument blanks?
Okay, so yeah, so firstly, we know how many features we extracted from all the data sets. So we define those feature numbers, and we generally use a very low feature number. So often we're going to use kind of 20, 30 different features. The other thing we do is we subtract all the background information. So we do a pre-filter, and we also have air blanks, which we use and subtract those air blanks from the real sample. So we take the air blank either just before the real sample or just after the real sample. And if you subtract those out, you get rid of a lot of the environmental effects. So then you're pretty certain that you've got your features are a chemical which has come out of the breath.
Okay, so we have time for two very brief questions. The first is from Chad. Were patients given Benadryl or any other antihistamines prior to biological administration?
I have no idea.
Answered in a direct way, unlike politicians, which is always good. Last question from Enrique. Gut microbiota is different in different geographical areas. Could it affect results in different populations?
Okay, so what I would guess is that, after kind of many years, it is disease that brings people together, not health. So I would expect that even if you had people with different gut bacteria from different areas in the world, when they had the same disease, they would actually move closer to each other. And I find this a lot when we test ethnic diverse groups within the UK who are, from Asia, Africa, etc. So their kind of general biome is very different, but in disease they come together.
Okay, excellent. Thanks for that. So there's a couple more questions that James will answer just on the typing them into the responses. We need to shuffle along for time reasons. Thanks again, James, for that. Much appreciated.
That's it. No problem. Take care.